related topic. So go down, we go for the you. I'll leave you the floor.
Yeah, thanks so much, Pascal, for the very kind introduction and kind words, and for the invitation, of course. Pascal has been great. Cami also deserves a shout out, who's done an amazing job with logistics. Primarily, it's great to talk to all of you folks. It's also great to avoid the -20 C temperature back home. So appreciate that. So yeah, today I'm going to be talking, as Pascal said, about efficient private mean estimation. This is based on a paper with a much scarier name, but it, you know, when you send it to a theory conference, sometimes you have to intimidate a little bit. So I apologize. So let's keep it. It's a very simple problem. In fact, this is kind of focused on the most basic statistical task, which I think it was surprising to me that we didn't really understand this to the level we did. So you don't need to know anything about differential privacy. Well, we're going to start very simple. So let's also say that you know, if you have any questions, anything's unclear, we can tell. This is a very leisurely time talk, in my opinion. So you know, happy to take any questions online if we want to clarify something. So please don't be shy. This is joint work with my friend and collaborator Sam Hopkins, who's now faculty at MIT, and Mabod Majid, who's very sadly not my master's student anymore. He's now gone on to his PhD at CMU. This may be the first time you're hearing his name, but it will certainly not be the last time you're hearing his name, because he's outstanding. Yeah, and a lot of credit goes to him for this. Cool. So yeah, like I said in the abstract of this talk, that no, you know, assumption of anything, any knowledge of differential privacy would be assumed. So we'll take it very slow. But let me start with a sneak preview of today's talk to just give you an idea for what the big result is, what the main result is. So we're going to give you, I'm going to tell you about an all-in-one, as I like to call it, private mean estimator, which is going to have a lot of different desiderata. It's going to be computationally efficient, it's going to be private, and it's going to have near optimal sample complexity. And as we'll see, that these are three natural things you would want for a private estimator, but there was nothing before that could give it for this specific case that we care about. But beyond that, we'll see that this also has a really interesting tie-in with some exciting trends that I've been working on, as well as others, in efficient multivariate high-dimensional statistics, such as robustness and something called sub-Gaussian rates, which we'll revisit a little bit. So, you know, this might sound like, you know, maybe just one niche thing, you know, private mean estimation, only if you care about privacy. But no, I think this is really part of a broader trend that's been going on for the last, like, roughly 7 years. So I think that's really exciting that we found another frontier for this line of research. More broadly, I think, like I said, this is a very embarrassingly basic question that I think we address. And so it tells us that really there was something we were missing before in our understanding of how to do private estimation. And yeah, like I said, this is part of the same research agenda, I think. And hopefully this work is just the first step, and it serves as an invitation to multiple communities, in particular, you know, the robust statistics community, the sum of squares optimization community, and so on. So yeah, this is just a slide, the talk in one slide. We'll take it step by step, though. So first of all, I said I wouldn't assume anything about privacy. And so the natural question is, what is privacy? And the type of privacy we're going to be concerned about today is, how do we ensure that statistics don't leak information about individual data points? This is a big problem in a lot of statistics and machine learning. For example, there's some really nice works in machine learning which say that machine learning models, when trained on sensitive data sets, can in some cases essentially regurgitate sensitive data. And, you know, GPT-2, GPT-3, and other talks I might have had you know, pictures of this which show that, you know, training data can be leaked. I didn't in this talk, but even in more basic settings, like even mean estimation, turns out that you can find out certain data points, whether or not they were in the data set, which is bad if these are sensitive data points. For example, whether or not you participated in some sort of medical trial for a rare medical disease. This is naturally something you'd want to be protecting someone's presence in this test. So there's a lot of ways to try to approach this sort of broad question, and seemingly the main solution that many people focus on is differential privacy, introduced by Dwork, McSherry, Nassim, and Smith in 2006. There's a very popular notion of data privacy. In particular, it's used in a lot of companies, Google, Apple, Facebook. It also was notably used in the 2020 US Census. So pretty much anyone in this room who was here in April 1st, 2021, or 2020, their data was passed through a differentially private algorithm in the US Census. But taking a step back, what is differential privacy? It's a kind of weird definition, and it takes a little bit to sink in the first few times you see it. So I'm going to give you sort of an intuitive picture of what differential privacy is, and then I'll show you the definition. But if it doesn't make sense, don't worry about the definition. It's not too specific. It's not going to be too relevant for the talk itself. Just trust me, that's a good one. So here's the caricature of how differential privacy kind of tries to protect data. So we imagine that there's some data set X, which is fed into an algorithm, sometimes called a mechanism, and it produces an output. But alternatively, we could imagine that there's a different data set, X prime, which was fed into the algorithm and produces an output. You see that these two data sets, X and X prime, are very similar. They only differ in one entry, which has been added, removed, so on. Now, the idea is an adversary is going to look at the output of this algorithm, and based on this output, then they have to decide whether the input data set was either X or X prime. And the idea is if we say that the adversary can't really tell whether X or X prime was the input, then the algorithm is differentially private. That's the intuitive definition. It tries to sort of mask the contributions due to one individual in terms of how they propagate into the output. So that's the intuitive definition. The mathematical definition I'll throw up here. It kind of says for all an algorithm is differentially private if for all inputs which differ in one entry, sometimes called neighboring data sets, then essentially we want that the distribution of outputs that the algorithm produces are similar in some way. And I've kind of masked it here, but really it's something like this. It's a multiplicative factor, an additive factor, and you really have to think for a while to understand why this is the right definition. But I'm just going to propose it, and yeah, I'll pause here for any questions about the definition, or at least the intuitive idea behind it. Good drink of water. One natural question that everyone's shy to ask is, why a goose? Why are they the adversary? Come to Waterloo and you'll find out. Okay, anyway, again, that's the definition of differential privacy. The specific definition isn't too important. Just trust me in saying that this is a rigorous notion of data privacy, which kind of hides the contribution of single individuals. Another way of wording differential privacy is there's some quantity called the privacy loss random variable, which essentially quantifies how much information is leaked about, whether it's from X or X prime. So what differential privacy says in another way is that the privacy loss random variable is bounded with probability, bounded by epsilon with probability 1 minus delta. So, oh yeah, I should probably tell you that epsilon, you can think of that as being like a number. It's a quantitative definition. So think of it, epsilon as being about 1 or something, whereas delta is going to be very, very small. And the reason is because maybe, essentially your privacy breaks with probability delta is an intuitive way of thinking about it. So there's two notions of differential privacy which are often considered hand in hand: pure differential privacy, which is delta equals 0, and approximate differential privacy, delta greater than 0. And you can see that, essentially the former, pure differential privacy, is the strongest notion of privacy, differential privacy, because it essentially says we know that the privacy loss will always be bounded. Whereas approximate DP says that, maybe things go wrong once in a while with some small dependence on delta. It turns out that these are actually very qualitatively different notions, that there are things you can do with approx DP that you just can't do with a pure DP. And this makes it a lot harder for algorithm designers if you want to guarantee pure DP, because there's just a lot of options which are not on the table anymore. So yeah, today our goal is to focus on pure DP algorithms. There's some things which are known for this setting in approx DP, but pure DP is kind of the strictest notion, and we'd like to understand what can or can't be done in that setting. So that's basically everything you need to know about differential privacy. Strong notion of data privacy. We're going to focus on the case when delta, the failure probability of the privacy guarantee, is essentially 0. Is 0. Yeah. Yeah, right here. Yeah, delta is kind of the additive thing. You might, a natural first thing to wonder is, why do you need this multiplicative term? Can't you just have a delta? But it turns out that is, we can talk about some like silly cases where, having, say, just a total variation guarantee with the delta is going to be disastrous in terms of privacy. So you kind of need both epsilon to be a small constant and delta to be pretty small. Say 1 over n is what you can think of delta as being. Cool. Yep.
So you have an understanding of like when is delta, like when I can work with just pure differential privacy, and when do I have delta greater than 0?
Yeah. That's like the question is basically when is pure DP and versus a prox DP? What are the separations and similarities between them? That's a very interesting question, and like it kind of differs from problem to problem. And I think one of the most surprising results for the DP community is the fact that for most of the cases that for many problems, there's separation, like polynomial separation between these two notions. The very surprising thing is actually that we showed in this work that essentially there's no separation for this specific task we're going to look at. But in many cases, it depends on a problem-to-problem basis. Cool. Any other questions? Yes.
Is there any assumption on that one entry, like as a boundary?
Yeah, like the question is kind of, what does it mean to differ in one entry? And this can vary from what depends on your problem. Like, for example, you can say that the data set is unbounded, and so maybe one change is just moving one point to an arbitrary other point. But depending on your data setting, it's up to you as like the algorithm designer and the data curator to understand what exactly the neighboring definition is appropriate. Great question. But we'll see for our particular setting today what the appropriate one is. Yeah. So what is the probability over here? So yeah, great question. Because this definition as focused is just on for a specific data set, one particular data set. So all the randomness is just in the mechanism. We're going to have another source of randomness later on because we're going to be looking at random sampling for the data set we get. But at least in the definition of differential privacy, it is worst case over all data sets. So no matter how weird your data comes out due to random sampling, we still want privacy, which is kind of natural because think of it, maybe if your assumptions about your distribution are incorrect, we don't want to just give up privacy. We want to, like, that doesn't seem very convincing if you're someone giving your data up. Cool, fantastic questions. Anything else? Cool, so that's DP. Now, the problem that we're going to consider today is mean estimation. One of the most, in my mind, either the first or second most fundamental task in statistics. And we're going to see that even for this very basic problem, things get hairy kind of quickly. So let's start non-privately. Here is the setting that we're going to focus on for this talk. I'm going to pause for a bit after the end of the slide to make sure the setting is 100% clear. But we're going to imagine we're given a data set, x1 through xn, drawn from some unknown distribution p, which is d-dimensional. So our data will be d-dimensional. And what do we know about this distribution p? We just know that it has bounded covariance. This is the sort of the mildest assumption we need. And our goal is to output some estimate of the mean such that the L2 distance between the true mean and the output of the mean that we give is of most alpha, I would say probability 99%, high probability. And so non-privately, this is very easy to solve. You just take the empirical mean of your data set and you can just, it's not too hard to show that the amount of data you need to solve this problem is d over alpha squared samples. Some of you may prefer rates. I know there might be more statistically minded folks in the audience. And this is really the same thing if you just swap the position, you invert the equation in terms of like alpha and n. So I'm going to flash rates on this slide, but not further than that. So this is the first algorithm you think of, and it works non-privately. I'll comment that there's some more stuff which some insiders in the room might be aware of. If you want really high probability of success, not just 99% probability of success, say 1 minus beta, you can get a sample complexity with an additive log 1 over beta, or in rate form like this. And it's surprisingly non-trivial to get this plus log 1 over beta. This is called sub-Gaussian rates by the statistics community. The statistics community really cared about this type of problem. There was a nice work by Gaussian Mechanism, which gets this plus log 1 over beta. And it's made efficient by Sam Hopkins in previous work. Naively, if you just do it without, then you get a multiplicative 1 over beta. But getting this plus log 1 over beta is an interesting thing. But it's not too big a deal for now. We'll eventually see later that we're going to get this for free. But yeah, so this is essentially what we know about non-private mean estimation. And for today's talk, for some technical reasons that come in due to privacy, I can talk about them later / offline. I'm going to pretend we start with a warm start, a coarse estimate of the mean that is up to like, a polynomial sized ball. I put root d, but you can imagine d to the 50, d to the 100, any sort of poly d coarse estimate of the mean. So yeah, but this is sort of like the non-private setting for mean estimation. Very simple, very well understood. I'll pause here in case there's any question about the setting, because it's only going to get more complicated on top of this. Yes?
How would probability with respect to the n samples that you get?
Right. So great question. Here in this setting, it is 99% with respect to the samples that we get. In particular, it's just a deterministic algorithm. But more generally, later on, we're going to want it with, say, high probability 99% with respect to A, the samples, and B, the mechanism itself, the random algorithm. Exactly, yes. It's necessarily random by the definition of DP. But good, yeah. So the utility will want randomness over both of them, whereas the privacy will want randomness only over the algorithm. Great question. Any other questions about the setting? Cool. So let's put this in this very, conveniently sized table, which we're going to revisit later, a few times. So empirical mean is great because it has linear sample complexity. That's a key thing I want to focus on. The fact that we have d-dimensional data. We need order d samples to get a good mean estimate. The running time is very efficient. You just take the empirical mean, poly time. But the bad thing is there's a talk on privacy. This is not private. We could talk more about how to attack it. But yeah, hopefully it'll be clear that this is, we didn't do anything. It's a deterministic algorithm. It's not differentially private. So we're going to go from there, try to fill in other rows in this table to see other approaches. And this is the rough outline for the talk. And in particular, I'm going to focus starting on 3 deficient private algorithms, and then we're going to see how to make things work out. And so with apologies to Tolstoy, we'll see that every flawed algorithm will be flawed in a different way. Yeah, and so this next part will take us through kind of the basics of differential privacy, since I didn't assume anything, but we'll see 3 natural algorithms that anyone who's taken a course in DP would consider trying to attack this problem. And so I apologize to those of you who already know DP, but I'm just going to tell you, oh yeah, question. Correct. The empirical mean is not differentially private. In particular, there's no epsilon and delta which satisfy that inequality. And the easy way to see that is because, like I said, the probability there is only over the algorithm, and the algorithm is deterministic. So, different inputs will give different outputs with probability 1, or they can. There exist ones, right? Does that make sense? A simple case, suppose you have like some numbers you add together, and then you add one point, which is a huge outlier, 10 million or something. The mean will obviously be different, and you can tell those 2 cases apart without too much trouble. Cool, but we'll see some private solutions. And the most basic thing you'll learn the first day of any privacy course is the Laplace mechanism, which essentially, giving the cliff notes of the slide, is you add Laplace noise proportional to the sensitivity of the statistic. But in a bit more detail, let's say the setting we care about is, suppose we have a function or an algorithm, which is it takes in a data set and outputs some d-dimensional vector. For example, like a natural thing is a non-private mean estimation algorithm. So think of that as, say, a running example. And this is the L1 sensitivity of the function, which is a bit intimidating looking, but let me just try to unpack it for you. So the idea is we take this function f, you put in a data set, you change one entry of the data set and see how much the function changes in L1 norm. So this kind of tries to quantify, imagine adding or removing one data point to the data set. If it is very sensitive, then delta, capital delta here, will be large. If it's an insensitive function, that is, it shouldn't change much, then delta would be small. And naturally, this kind of indicates intuitively how easy it is to privatize something, right? If a function is very insensitive to adding one person's data, then maybe it's easier to privatize. If it's very sensitive, it jumps everywhere when you add people's data, then it's harder to privatize. That's a natural intuition, and we'll see that's kind of how it works. Yeah, how much can the function change by modifying one data point or adding, removing? They're all kind of the same. And the Laplace mechanism, like I said, this is kind of the first private algorithm you'll ever learn, is essentially saying, take your non-private function, you add Laplace noise to every coordinate. I guess I have it in words here. Yeah, you add Laplace noise to every coordinate where the size of the noise you add is proportional to the L1 sensitivity. So again, the more noise more sensitive it is, the more noise you have to add, and so on. And again, the more private you wanted, that is with a smaller epsilon, the more noise you have to add as well. So in case you're not familiar with the Laplace distribution, there it is at the top right, kind of a two-sided exponential. But the takeaway from this slide is you add noise proportional to sensitivity, and in particular, for this case, the L1 sensitivity, which is kind of a technical point, but it'll make a difference in the future. Yes?
So there's no notion of, this is just like theoretically the max in that L1 sensitivity. So could that be like, if my distribution is normal distribution, theoretically it could go to infinity for means.
Perfect. Yes, yes. That's an important thing. This is a max over all data sets x and x prime. So that is every possible data set. It doesn't depend on your distribution at all. So you're totally correct in the sense that, say you have a Gaussian distribution, you see a point at 0, and just add a point at infinity, and that's going to totally mess us up. And we're gonna see how to get around that. But yeah, it's a worst case over all data sets. Yes.
Laplace distribution to add noise. So is it suggesting that any heavy tail distribution will work, or there's some property of Laplacian distribution which will be?
So good question. Why the Laplace distribution? If you stare at the definition of differential privacy enough, you'll see that essentially this is precisely the distribution that makes it work out. There are other things which imply it as well. We'll see Gaussian noise also works with slightly different things, but yeah, essentially it matches the definition. Great. Any other questions? Cool. So this is the first algorithm you'll learn in differential privacy. So let's try to use it on mean estimation. And as pointed out by one astute gentleman there, things are going to fail pretty badly, but we'll see how to correct that. So the empirical mean is, the average of your data points. The sensitivity is infinite, right? Here is a data set where I took 1 point, moved it off to 1.8 times 10 to the 308, kind of the biggest real number, using whatever floating point precision. And yeah, so this is going to totally mess up your statistic because the sensitivity is enormous or infinite. This will necessitate amounts of noise which totally drown out any sort of signal you would have in your data set. But fortunately, the solution is not too hard, at least on how to get around this. Use the clipped empirical mean, which will essentially, what the clipped empirical mean is kind of what you guess, right? You clip your data points to some L2 ball of radius square root d, which if you know, like, high dimensional concentration, roughly most, if not all of the points should appear within this radius. It's not totally trivial, but just trust me when you get most of the signal, if you do this, there's some bias, you can control the bias. We showed this in some other work. But yeah, this is a very natural way. Essentially, any point that's too big, clip it in some data independent way. And then that's very nice. So like if you are pre-processing your data by clipping it in this way, like I said, that will limit the sensitivity. And now it's not too hard to show that the L1 sensitivity of this clipped empirical mean is now bounded by, say, d over n. And that gives us an algorithm which is very simple to privatize the statistic. It's called the clip and noise thing. That's what we call it sometimes, where you clip the data points and you add Laplace noise d over epsilon n to each coordinate. So it's not too hard to see here. If you're adding noise of magnitude roughly d to each coordinate, then the total amount of noise you get in L2 norm will be d to the 1.5, because it's d in each coordinate. So and it's multiplied by a factor of root d to account for the overall L2 error. And so as a consequence, we get that the resulting sample complexity from this algorithm, that is, if we want to cancel out this noise so that it becomes small, we really need n to be at least d to the 1.5. So let's take stock of where we are. I talked about how to apply the Laplace mechanism here. And you'll see that this is a very easy algorithm. It's poly-time. It's clip and noise. That's very easy to do. It is also like I said, I didn't prove it for you, but it is also a pure differentially private algorithm because the Laplace algorithm, the Laplace mechanism is pure differentially private, so that's good. But the bad part, the really thing I want you to hone in on here is we were adding so much noise here that now the sample complexity went from D to D to the 1.5. So now we had to pay extra due to privacy, which is something we were trying to avoid. We'd ideally like to maintain an ordered D sample complexity, and we failed at that. Cool. So any questions about this approach and the drawback of it?
I have a question. I'm remote.
Great. Yeah, that's a good question. You have to. I appreciate you called me out on that. Remember, I said we start with a coarse estimate of the mean, and it turns out, if you assume that you know the mean up to about root D, then you expand that ball, like put a radius of 100 root D or something around that coarse estimate, and that should probably contain everything. Good, great question. Very insightful. And we need that for technical reasons, which I'm happy to talk about offline. Cool. Anything else here? Cool. That's one simple algorithm. We'll see the second algorithm is very similar, which is the Gaussian mechanism. This is almost exactly the same thing. There are some crucial diffs, which I will highlight. Essentially, you add Gaussian noise instead of Laplace noise. And this has some important but relatively minor differences in the sense that first thing that happens, if you just trust me on this, is that you have to add noise calibrated to the L2 sensitivity rather than the L1 sensitivity for this. L2 sensitivity is in general less than L1 sensitivity. And in particular, it can be square root D smaller than the L1 sensitivity, which is a good sign, right? Because we were off by a square root D factor. Maybe we can save that here. The downside, so in fact, we do save exactly that root D factor, and it becomes a sample complexity of order D, essentially. The downside, though, is that the Gaussian mechanism is kind of a lighter tail distribution. So naturally, this is less private than the Laplace distribution. In particular, it's only going to give approx dp rather than pure dp. So returning to our table again, essentially, if you add Gaussian noise instead of Laplace noise, it's great that you save this root D factor. You get the right sample complexity, but you now hit this approx dp weakening of your privacy notion, which is, it's nice, but it's not what we were going for. So somehow we paid something to get this better sample complexity. Pause for a second again. Cool. So now, I guess you can probably bet which column will be read next. And we're going to show you, I'm going to show you a different algorithm, which is, in terms of flavor, very different than the two we've seen so far. These two have been noise addition, which is very intuitive and natural. The next one, called the exponential mechanism, is a little bit trickier, a little bit different. So this kind of differential privacy 102, so to speak. And the idea here is this is useful for private selection of objects. I'll say it like this: privately selecting an object from a set based on score, kind of a type of optimization-based perspective. So here's the setting abstractly, and then we'll see how to apply it to our setting. We're going to imagine that we're given some sensitive data set of n data points. We have a set of objects Q, which is publicly known. And we're going to have a score function, which takes in the sensitive data set, takes in an object, and tells us how good that object is measured by a real number. This is a little bit abstract, but I'm going to make it very concrete in the next slide. And so the goal here is, given this kind of score function, the sensitive data set, we want to output an object which is approximately maximize the score, kind of one of the best, highest scoring objects. And it turns out the exponential mechanism is a random sampling thing, where you sample one of these objects randomly, where, don't worry too much about the specific form, but essentially you sample it higher probability if it has a high score, and lower probability if it has a low score. Very natural, in my opinion. Again, this is a little bit, and this turns out it will give us the stronger notion of privacy we want, pure DP. Like I said, this is abstract, so let's go with a specific concrete example where I'm going to imagine running an election as a canonical example of, we want to run an election privately. So like I said, we have a set of objects who are the election candidates. In this case, we're going to use the authors of this paper. The sensitive data set is quite naturally the votes for who they were cast for. And you can see a set of votes here, which, Mabod gets the most votes because he's the best. I get the least because, that's the way the world works. And the score function is very naturally the number of votes for each candidate. So if you didn't care about privacy, then you would quickly realize that the highest score is Mabod. Since he's the best, he's selected as the best candidate. But the thing is, this is not very private in the sense that if one person changed their vote from Mabod to Sam, then instead Sam would be the best. So this is not a private method, and instead what the exponential mechanism prescribes is instead to do a random choice of who wins this election. Maybe not the most popular in the real world, but at least for the sake of differential privacy, it works. And so, I calculated some probabilities of being selected as the winner of this election with epsilon equals 0.1. And you can see that there's a 24% chance that I actually steal the victory from the jaws of defeat here. Cool. So that is, you assign scores and use them to noisily pick the winner. So you can think of it as a noisy election type procedure, if that's the most convenient way, rather than the abstract picture I used before. So this is the most important of the mechanisms we're going to talk about because it's going to be the one that gives us the final algorithm in the end, we'll see. But if there's any question about the setting of how this kind of algorithm works, I'm happy to take them now. Yes? No, that's a great question. You compute the score non-privately, and then all the privacy comes in when you do this random sampling. But great question, because it doesn't have to be private at all. One thing we're going to need for technical reasons, it has to be low sensitivity. That is, changing one person, the score shouldn't change much if you add or remove one person's vote, which it doesn't in this case, but more generally, it has to be low sensitivity. But it does not have to be differentially private. Great. Cool.
So in order to sample here, you have to have an agent that receive all the scores and then sample from this, right?
Yes.
You're not privately specified.
Great, yes. So all of this work today that I'm talking about is in the trusted curator model, in the sense that there's one person or one party who you trust with the clear data without any privatization applied. This is perhaps limiting in the sense that maybe you don't even trust anyone if it's a very, very sensitive. There's a stronger model known as local differential privacy. But for example, in the US Census example, we kind of trust the US Census as the curator for that case. But yes, you do need a trusted curator. And in fact, this algorithm just doesn't work. Like you can't really, there's some things you can do in central, the trusted curator model that you can't do in the local model because you can't run this algorithm. Great question. Any other thoughts on the exponential mechanism? Again, the sort of takeaway is assign scores and use them noisily to pick a winner. That's the main thing you should take away from this. Yeah. Yeah.
So this, you have like assigning scores and all. Can it always be mimicked by adding some kind of noise? Like,
great question. Yeah. So actually, this is a very generic algorithm, and in particular, it generalizes the Laplace mechanism. And there's also a way to view this as an equivalent thing is to compute the scores for everyone and add Gumbel noise to their scores for whatever reason, and then pick the thing with the highest noise score. That's called the Gumbel max trick, actually, like if you're familiar with the thing. But yeah, so you can kind of view this as a noise addition thing, and they're kind of equivalent in some weird way that is still a little bit arcane to me, but yeah. Cool. Great questions. So we're going to see how to apply this in this setting. And the idea is that this is going to be a sort of net-based argument, if that is familiar to you. Was there a question? I saw something pop up briefly. I don't know how to, can I go to it? There was one question about, is score typically convex? Fantastic question. Someone like, the score can be arbitrary for now, but we will see later on that having our score function satisfy a number of nice properties will be very useful. And for particular, let us make this efficient, because right now we're going to see an inefficient algorithm. So yeah, this is kind of a net-based argument for now. And we'll see why. So the intuition that we're going to try to exploit here is the fact that the empirical mean should be close to the true mean in every 1D projection. This is a fact, I'll tell you, and that's the intuition we're going to try to use. So for example, suppose here's our high dimensional data set. You have data points in some sort of spherical shell. And this point here in red, if I told you, hey, this is the mean, you'd very quickly call me out and say, no, that's not the mean, because here's a 1D projection, and you can see in this 1D projection, it's not at all in the center of the data set. It's very far off to one side. So this is evidence that this is not a good mean. It's not the mean. On the other hand, if I tell you this point, then take a look at any 1D projection. I picked one of the many possible ones, but you'll notice that this point is roughly in the middle of the data set. So this kind of intuition will lead to our score function, which is a little bit of a mouthful. Like, I'll try to say it's the number of points you would have to change to make this be close to the center. Like this one, don't touch it at all. You'll see that this is like very far off out at the edge of the data set. So it's got a low score. Whereas this thing in the middle, my claim is it's not only in the center of your data set, but you'd also have to move a lot of points to make it not be in the center of the data set. So it's kind of robustly in the middle of the data set, which is why it has a high score function. So yeah, kind of the score function is how deep is it in the data set. If you're familiar with the Tukey median, this is or the Tukey depth of a point, this is kind of related to what we're doing here. Similar idea. So this is a nice score function for the sake of, it's a low sensitivity and it turns out to capture what we want. The bad side is, as I describe the score function, it seems it's not obvious how to compute it. Like you have to look at every single projection, every single 1D projection to compute it. So it's not obvious how to compute that in the first place. The next thing is how that's just computing the score function for one point. But I said you have to compute the score function for every candidate and then pick one and then sample from a probability distribution. So essentially, you have to, your objects that you're going to use here, that is, we're going to try to pick one of these points in space to be the mean that we output. And it turns out that there's a lot of them. There's 2 to the d different points, which could be a good output of the mean. So yeah, like to summarize this, there's a lot of different candidates we'll have to consider, a lot of different objects, not just 3 like we had in the election case. And each one to compute a score function is also computationally hard. So these are the big computational issues we'll face. But let's put those aside for now. At least the nice thing is that the sample complexity is not obvious, but this will give a linear sample complexity or near linear sample complexity O of D. Yeah, and I'll skip this point. So yeah, here's the second last row in this table where we can see that the exponential mechanism, it gives us something with the right sample complexity, it gives us something with the right privacy notion, but for 2 different reasons I highlighted, it is not computationally efficient. So we've seen now, you have a question about exponential mechanism?
The definition of the score is now like look at the worst possible direction. In that direction, take the projection, and then how many points would you kind of move?
Yes, yes, exactly.
Okay, worst possible direction.
Yeah.
There are like these DPPS methods.
You're familiar with this stuff. Yeah, that's kind of going to be our escape rope from this issue, but not the only one. Cool. So yeah, and perhaps you can see what's coming next. I'll tell you about our main result. I think you can fill in what these should be. Essentially, we get the best of all worlds. We get something with near linear sample complexity, pure DP, and a polynomial running time. I will flash, this theorem here and pause for an awkwardly long time, because if you get this theorem, then I think you get the main result, and then I'll spend the rest of the time telling you a little bit about the techniques and also what the algorithm is, and maybe a little bit about the bigger picture, which I think is kind of nice. Cool. So again, I'll pause until it gets awkward. For any questions? Yeah.
Like how important is the age? Like what if I measure error is hard or not?
That's a good question, and I've kind of been wondering, like, there's some gaps between, I mentioned the gap between pure and approx DP, and I'll say I don't know, and I think it's an interesting question, but I haven't looked into it yet.
Even without differential privacy sample complexity. Do you understand that for other nodes?
Do we understand that? I don't know if any specific paper, but I feel like it's probably folklore stuff. I don't think it's super complicated. I think the empirical mean is the right thing to do because what else would you do? But yeah, I don't know. I think it's a good question, which remains to be explored. Any other questions? All right, that's awkward enough. Let's continue. I'll spend the rest of the talk, telling you the ideas behind fixing this. And it's the third method which we're going to fix because it was kind of the closest to working in some sense. It was, the only problem with that was inefficient. So we'll see how to fix that. And there were two reasons why it was slow. One reason was because computing the score function for a single candidate was slow, which, Sahil spoiled it. And the solution will be some of these recent advances in robust and high dimensional statistics. The second problem was the fact that, like I said, we're going to compute, if you want to compute this distribution over all the different candidates, you have to compute the score function for each individual candidate. And then there's exponentially many, so computing the normalizing factor. Like all of this just seems like a little bit of a pain. But the nice thing is there's been a lot of work on efficiently sampling from log concave distributions, which will save us on the second part. So I'll go through each of these, not too much detail, but yeah, like drawing this back to something I mentioned in the first slide or first few slides is that there's been a recent work on robust multivariate statistics, which essentially tries to solve exactly this problem, finding interesting directions efficiently. For example, one desideratum is robust estimation, where you say 1% of your data is corrupted. Can you still deal with that? And we had some work as well as Lai Rao and Vempala, work done right here at GT back in 2016 simultaneously. Yeah, I didn't know until it was posted to arXiv at the same time, but very, very cool. So these works deal with polynomial-time algorithm for these problems. Also, the stuff I alluded to earlier, sub-Gaussian rates, which look at trying to get this plus log 1 over delta, or sorry, log 1 over beta in the sample complexity. This also seems to be based around similar ideas. For example, essentially following up on this Lugosi-Mendelssohn work, which was inefficient, Hopkins made it efficient via somewhat downstream ideas from this robust estimation works. And I think the really cool thing is this is like another case where the same ideas are very useful in terms of getting a third desideratum of privacy. So there's some works which did it simultaneously with us, but I think there's probably more to be seen out there. So let me try to give you an idea how we use these ideas. I won't go into too much depth just in the interest of time and talking about other things, but like essentially we're going to change the focus a little bit in the sense that before the way I described it was trying to like look at all different candidate means and pick which one's the best. But now let's relax it a little bit or do something a little bit maybe easier where I give you an estimate of where the mean is and I want you to kind of point towards the center of the data set. Kind of say, just to draw a quick picture. These are permanent markers. I'm not going to do that. Here's one. Yeah, suppose our data set is something that looks like this, and we have points over here, and I tell you our current candidate is here. Then the idea is I want to privately find that this is a good direction to move in, and that's probably a better mean. So kind of pointing towards the middle of the data set privately. And this uses ideas from this work by Hopkins and follow-up work by Cherrapunam-Jerry et al., which is chronologically, seems awkward, but stats journals take a while to publish. So that's why it's that order. But anyway, yeah, the idea is there is some quadratic optimization problem which you can define, which kind of tells you how good a particular direction is. That is, in this picture I drew here, this arrow would hopefully have a high score, a high solution to this optimization problem, whereas something orthogonal would be very low or poor because that's not a good direction to go in. And so I'm not going to walk you through the quadratic program at all. Like I could, but in the interest of time, I'll sort of skip it. But it kind of tries to find a good direction in that way. Now, as you should know, that quadratic optimization problems are not efficiently solvable, but fortunately, these works, they looked at a SDP relaxation of this, and it is possible to solve a relaxation of it efficiently. So yeah, that's going to be the first idea we're going to use. We can compute a score function efficiently for something related to what I was saying using these recent advances. Yeah.
It's a relaxation. It's not the original score. You changed.
Yeah. We're doing something different from what I showed you a few slides ago. Even the quadratic program is kind of different. But yeah, it's not super different. Like, it's based around the similar intuition at least. Cool. The other thing we will get around is, like I said, there are many candidates. So even if we could do the score function instantly, computing it for all the exponentially many candidates is also expensive. But if you take a look at what the exponential mechanism does, e to the epsilon times the score function, there was this very astute question in the chat asking if the score function is convex. And in fact, like, the idea is you'd actually want it to be concave, because if the score function happens to be concave, then the resulting distribution will be log concave. This is like immediate. And once you make this observation that you have a log concave distribution here, that's when you can import a whole lot of really awesome work from classical computer science and statistical work, which essentially says that you can efficiently sample from log concave distributions, assuming some other conditions as well. So yeah, there's been a lot of work done, including here at Georgia Tech. There's some caveats here. In particular, like, usually you look at total variation guaranteed. We need a multiplicative thing for the definition of DP. But fortunately, this was handled by Basili Smith-Vikurta and also some recent work by Mangubi and Bishnoi. But yeah, effectively, the idea is, instead of naively computing the score function for everything, because there's exponentially many, we can use some of these tools for efficiently sampling from log concave distributions. Yeah, there's some other minor technical things which I'm not going to get into, but that's the main idea. And this essentially says, I'm going to skip this in favor of going to this algorithm, which gives you a picture of what actually happens in these algorithms, which is, this really stretched the extent of my artistic skills. But I'll show you the algorithm first, and then I'll give you an amazing animation of it. The basic idea behind the algorithm is very much like a gradient descent type algorithm, where we essentially find a direction, kind of like this picture that I drew on the board here. We're going to find a direction that we think will point towards the mean. We're going to step in that direction and then repeat. Like, to go back to this picture, maybe we move here to this dot, and then we see from here, okay, maybe going in here is also a good thing, and eventually we'd get to the middle of it. Now, you see I left some big blanks because it's not obvious how to find this direction. But that's kind of, finding the direction is where pretty much all of the technical work goes into. Like, we use the exponential mechanism with efficient sampling to pick this direction we step in. And then this is via random walk, because that's how these log concave samplers usually work. And then we don't worry about that one. But yeah, to illustrate it with my amazing animation skills, you can see, imagine we start at this red X here. And the idea is that we are going to do some random sampling to find which direction to go in. So each time we look at one of these directions, this is computing the score function of that particular direction. And it turns out if you do the sampling, it amounts to basically, random sampling directions. And then eventually you settle on one which has a high score function. And then you take a step. And then you repeat by running the exponential mechanism again and iterate. And that is the whole algorithm, essentially. It's each finding the direction is kind of where all the technical work goes into, but after that, it's not too hard. Cool. And so we have a kind of meta-theorem talking about when we can apply this SOS exponential mechanism. Just run this exponential mechanism in an efficient way. We can write a bunch of technical conditions if these all hold. I'm not going to labor these. Then it's possible to efficiently use the exponential mechanism to get a high utility point. And this is a little bit of a mouthful if you look at it technically, but again, I'm going to skip this. But just I want to emphasize that there's something more general here than just this specific problem, which could be useful for other places you want to use this type of optimization techniques. So yeah, the overall theorem we produce is something like this, which is similar to what I showed before. Essentially, given this includes all the desideratum that we wanted, and beyond just what I talked about today, but beyond the privacy, it also is computationally, or sorry, it is robust and achieves these heavy tail or sub-Gaussian tails, even in other settings. So I'll pause here again if there's any questions about this. Yes. Yeah, the lower bound, good question. Oh, sorry. One thing I'll comment here is you'll notice that I gave one of the things we need is we have a bound on the mean of R. Like before I said, just imagine we have a bound of square root D. Now I'm going to parameterize it additionally in terms of how good our coarse estimate is. And so that shows up in the bound if you're curious what R is. But yeah, there's techniques which have been established for proving lower bound based on packing lower bounds. That's kind of the buzzword. And I'm happy to talk more about what that means offline. But yeah, there's new lower bound techniques for the differentially private setting that come up. Cool. And I'll just emphasize that in this work, we were off by kind of this red factor here, where in a more recent work with Sham Narayanan, who's a grad student at MIT, we improved this by removing it. This is kind of like the least important thing of this new work, so it's kind of silly to focus on that. Yeah, more important stuff for Gaussians, but also, yeah, I won't focus too much. I want to just give you very quickly a bigger picture going on here, which I think what makes this the most broadly interesting to me personally. And it's the fact that like these same ideas keep working again and again, which I think is really, really exciting to me. The fact that, you know, I mentioned the stuff on efficient robust estimation back in 2016, which downstream led to these efficient methods for sub-Gaussian rates, which Sam showed in his AOS paper in 2020. Which was made like they started with something inefficient and made it efficient using similar ideas. And then kind of more recently, or in parallel with some of this, in the sort of inefficient world, there was some stuff that we did on inefficient private estimation. But then once again, using these same ideas, you know, following this trend, we see that these ideas are sort of underlying all three of these desiderata. So I really think there's something more here and unifying, which I think is exciting. And I think we've scratched the surface. There's like, you know, it raises a natural question whether robust and private estimation are equivalent, which, you know, we have some privacy implies robustness. This is in a work by Christian Georgiev and Hopkins recently. And then our recent paper, which is on arXiv, which I hinted about with Sham, additionally, this shows that robustness implies privacy in some technical settings. So the sort of summary is that like robustness and privacy seem to be equivalent, but there's some important caveats which we haven't overcome yet. So I just hope this tells you that there's something more interesting here underlying these problems, which joins them all together, and two, there's still interesting work to be done here in case anyone wants to investigate or talk about it more. Cool. So in conclusion, I'll say that we give, again, our main result for this particular paper, the first one that I focus mostly on, is we give the first efficient algorithm for pure DP estimation, which is linear sample complexity. And we also get these other desiderata for free. I think really the most exciting direction is to understand connections between robustness and privacy for even this most basic of settings. And maybe from a more technical standpoint, where else can these ideas be used for private estimation? And so I'll conclude there. Thanks so much for your attention and the interesting questions. Cool.
The first two algorithms, they rely on that definition of sensitivity.
Yes.
And that sensitivity, when you had that slide with the max, if I view it as an optimization problem, you're computing the maximum value over any possible two changes in the data set.
Yes. I'll comment that that may not be obvious how to compute in the first place. The sensitivity could be up.
Assuming we can do that.
Yeah.
It's a very, 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 very robust thing to compute that. right? Because when you give the example of, oh, I'm going to set the height of the person to the maximum real number.
Yeah.
The probability that you would actually see that number in practice is dramatically low.
Right. It is a very pessimistic definition. Yes.
So I'm wondering whether your definition of sensitivity is very pessimistic in a sense. And if you were to somehow take into account, I don't know how to do it, but the intuition that I have is if somehow when you compute this sensitivity, you restrict the kind of changes that you have. You cannot go arbitrarily far, or you have to somehow, maybe you can inform that with the assumptions you have on the variance or something. I imagine that this would reduce the sensitivity that you have. If you have a lower sensitivity, you put lower noise, and then you need less samples to denoise. Right.
I would say that's kind of the idea behind this clipping idea, in the sense that, you know, clipping essentially says, okay, these huge data points, those probably are outliers. So yeah, that limits the sensitivity. So I'd say, yeah, clipping, I think it implements your idea. And another idea you could have is the fact that, you know, maybe there's sensitivity bounded with high probability, which is a little bit more of a dangerous territory, because then you get into different definitions of DP, which lose some technical properties, which are very convenient, but also like kind of the motivation I was giving before, where if your model of the data is incorrect, then you know, you might lose privacy, and you don't want to. If you really, really care about privacy, that might be a dangerous thing to do.
Yeah. So if I wanted to put optimization terms on this, what you currently have is viewed as a robust estimator, and then you have something which is more the distribution robust. You make an assumption about the distribution, you allow your data distribution to change within the distribution space.
Yeah.
And that could give you lower sensitivity while still giving you some guarantee about, you know, having errors on the assumption you make about the data.
Right. Exactly. Yeah. Yeah. Yes. I think that's an accurate way of breaking it down. Yeah.
I don't know how to do it, but
I mean, the talk is actually already making some of the distribution of the hypothesis. Right? Because there is this slipstream constant, there is the constraints on the variance.
Yeah, like we do assume that the distribution has bounded variance and that we have a coarse estimate of the mean, not exactly head on, but yeah, maybe up to some very loose radius.
I think it's interesting to see all the phrases like this, the Laplace framework. It's an interesting question.
Yeah. Cool. You had a question?
Yes. So you've proven these good complexity bounds. You show that the algorithm is polynomial.
Yes.
But then from a computational perspective, I look at it and I see SDPs, and it sounds very, very slow.
Yes. Please do not go and implement this. This is not a practical algorithm.
So how do you see the path towards a practical algorithm? Could this be extended in that way, or do we need techniques to get there?
It's a great question. I personally think like the exponential mechanism, if you care about utility, is probably going to solve all the problems in DP. That's my personal philosophy. You know, I don't have a technical way to state the same, but yeah, I think there is a big question on, in my mind, I see the future agenda about like going from using the exponential mechanism theoretically, which is very useful, to in practice, maybe relying on some of these log concave samplers and stuff like that. So ask me again in 5 years.
So we're going to stop here.
Cool. Yeah, yeah. Yeah, I'm here today and tomorrow. Tomorrow, my afternoon is relatively free, so please feel free to reach out and we're happy to chat more. Thank you again so much.
Thank you for a great